I think we're going to start now. So my name is Steve Guttenberg, and I am the audiophiliac. This guy's a rock star. Not only does he design speakers, he is a good speaker himself. Is that a coincidence? Did you plan it that way?
I think it just naturally evolved.
Okay.
It's actually good to see all of you here, because it means there's more room in my demo rooms upstairs for other people to be listening while you're down here.
It's all about you.
It's all about me.
So one of the things that's really interesting to me about Andrew's method is he's a speaker designer that designs complete speakers. The drivers, the crossover, and the cabinet. I'm sure there are others. I can't think of anybody, but I'm sure there are many others. But Andrew definitely has that qualifications. You check all those boxes.
That burden, actually.
Yeah, it's a burden, because if it's wrong, it's all your fault. So, but you seem to bear that pretty well. And you're very productive, because you're the only guy, right? It's all you.
Yeah, I mean, obviously there's support staff in like doing the mechanical drawings and construction like that, but I also go out to the factory to check quality and set up the measuring systems and everything. So there is, yeah, it's a large part me.
Right.
Me.
Now, I think your job would be gigantically easier if everybody's listening room had the exact same dimensions, the exact same furniture, you knew where the speakers were going to be relative to the wall, the kind of music they listen to, their electronics. It would be a piece of cake, right?
Well, it would certainly be easier, except the arguing as to what room it should be in the first place.
Okay.
You once you standardise the room. And there is an IEC standard.
Oh, there is? So there is a perfect room.
Both in terms of dimensions and treatment and reverb times. So technically you could say, I'm going to design for that room. It's just that, like I say, you don't know where it's going to be used. So that's where the variability comes in. And perversely, in a way, the car is the perfect environment for the designer in one way, because if you're designing for OEM, right, so you're designing for a system that the car manufacturer is going to supply in that car.
In a specific
Not
car.
some aftermarket thing where someone is kind of picking drivers and trying to design their own system, but if I've designed it for that car, I know what that environment is, always.
Right.
The only variable is how many people are sat in the car. So it means that, although it might not be an optimum environment, but then you could argue very few environments are optimum.
Right.
But it's consistent. And so I know if I've designed it for that car, it's going to sound fantastic.
The way you want it to
sound. The way
sound.
I want it to sound. And I will get back to that, but it is the way I want it to sound ultimately. It's me, it's always about me.
So we need to clone you, too.
Well, my parents already have.
Oh, right, you're a twin.
I'm an identical twin.
Right. So you and your brother.
Yes.
Yeah.
And it's interesting because he's left-handed and I'm right-handed, so what we're called mirror twins. But what's interesting also about that is basically we're born as a stereo pair, but the left and I'm sure my parents were glad that quadraphonic didn't exist.
At least your mother. So, and then it gets to the question of placement. And I find it interesting that not too many owner manuals really specify, or do you, distance from the wall to the speaker, optimum, what's acceptable.
You give vague ideas. You have to be vague because you're dealing with a vague situation. You know, every listening room is different, both in size, shape, amount of windows, where the doors are, furnishings, carpeted or not, bare walls or bookshelves. Every bit of that influences how it's going to sound. And sometimes it's counterintuitive. You think that if I move speakers a bit further out from the wall, I'll get less bass. But you might now be coupling into a particular room mode. So you'll get a honk at that frequency. Or you move them together or apart. And that affects both the imaging but also the bass. So there are some programs that you can get that you can feed in reasonably sufficient information and get an idea of where to start with placement, and then you're going to have to fine-tune from that. So when I'm trying to advise people, because I'm not in the room and all I can see is pictures, it's very difficult to say exactly what people should be doing. And this old idea of, like when you're locating a subwoofer, you put the subwoofer on your listening chair,
Right.
play some music, and then crawl on your hands and knees around the floor to find where it kind of sounds.
So there's there's a reciprocal relationship between you and the
reciprocity is king in acoustics.
I love that. Yeah.
It's fun. I can.
So wait, I just want to back that up. So you're putting the woofer in the listening position on the couch or chair or whatever, right? And then you are at the other end and you're moving around the room and you're hearing that bass as it would sound if you reverse positions, right?
And it's a hell of a lot easier for you to crawl around on your hands and knees than keep moving the subwoofer.
Right.
I was doing a setup for TAD when I first did the Munich show, and we got a new listening room, and it's like 40 foot by 40
Oof.
foot.
Wow.
Where do I put the system? So I made sure I've got very long speaker cables to the experiment where I can place it, so I don't have to keep moving the equipment as well as the speakers. But the speakers themselves are £330 each.
Well.
I have to waltz you kind of hug them, my speaker, and then you kind of waltz it around the room. I woke up the next morning, I tore my shoulder.
Yikes.
So you don't really want to be moving big subwoofers around, so that's one way of doing it, that reciprocity.
It works really well. But you know, Andrew and I have had many conversations over the years, and I had this thing of asking him about the parameters of a given design, and it came down to the box size, the low frequency bass extension that you wanted to achieve, the sensitivity, and the fourth one is impedance, right?
Yes.
So in other words, as you make the box bigger, if all the things stay the same, the band, it creates more bass and it becomes more sensitive. But everybody wants smaller speakers, so you always have to make the speaker as small as possible and juggle all those other factors, right? So in other words, you can't have a tiny speaker with lots of bass that's highly efficient and easy to drive.
Correct. And so that's the first decision you make whenever you're designing something. So it's this iron law, box size, bandwidth, efficiency. And you pick two and the other is given to you. And if we want to go into some simple maths, I can show you very well.
Illustrations.
Can you turn on the projector? I show you some complex maths, and then I'll show you just how easy it gets to show just how you do things, for example. So it's really interesting when you try and work out.
There we go.
Yes. See, I said I'd show you some complex maths. But the thing that matters. Hey look, I don't have a laser pointer, I have a laser measuring, so I can actually... Okay. It's not right. It's not right here. Okay, equation 7.7. All of that
It's my favorite.
boils down to equation 7.7, which says that the sound pressure level from a speaker is just a product of U, which is the volume velocity, so the rate of movement of the speaker, times frequency, divided by distance. It's that simple. And so when you actually start to simplify it, there you go. Those, and some constant, that constant is the density of air. Volume velocity times frequency is acceleration. So it's the acceleration of the driver is the sound pressure that you get from a speaker. Easy. So what is the acceleration of the driver? Well, it's volume acceleration. It's area times acceleration. Now force is mass times acceleration, one of the simple Newton's laws of motion.
This is why you're a speaker designer and I'm not.
Right.
Okay, just making sure.
Force on a driver is the BL product, so motor strength times length of wire times the current. That's easy. Current is voltage divided by resistance, and you end up with this. This tells you what the sound pressure response of a speaker is. Area times BL divided by mass and resistance. So if you increase the resistance of a speaker, you must lower the sensitivity of it. If you increase the mass, you lower the sensitivity. If you increase area, You increase sensitivity. If you increase BL, you increase sensitivity.
Bigger is better.
Except,
Oh, sorry.
right? So it would seem if you want a highly efficient speaker, just put a big magnet on it, lower the mass, and lower the resistance, and you've got a very efficient speaker.
All right.
I
But
know you like efficient speakers,
I love,
Steve.
yes, I will get to that.
Unfortunately, this is now a calculator which tells you what the frequency response is when you have different ratios of those quantities. And those are the optimum ones. And it gives a nice flat response. The purple curve is impedance, it's a closed box and a vented box. And I've optimized that perfectly. However, for a given size box, if I now say I'm going to lower the mass to get more sensitivity, the sensitivity will increase at the high frequency range. The level will actually go down in the bass. If I put more BL, same thing. Anything I do will increase the midband and decrease the amount of bass. There is one optimum ratio for any given box between area, cone size, cone mass, and motor strength that will give you the correct bass response. Huh. So that iron law is just fixed. And so those are the parameters I have to work with as the very first thing I decide about designing a speaker. Typically, well, how big can this speaker be?
Right. That's the first decision.
That's the first one, typically. And once I've set that parameter, I have to adjust everything else to get the right response. Now, I can change that curve to be higher. It's still the same shape, but moved up in frequency and up in level. But it still means I've got a nice shape, higher sensitivity, less bass. So, which do I choose? And what I've always explained to people is my choice, all about me again.
Well, it is about you.
Is that, especially with budget loudspeakers, what does extra sensitivity give me? It means for any given amplifier, I can go louder. Great, until someone tells you to turn it down. How often do you play at the extremes of level? It's nice to think you can, but most of the time you don't play very, very loud. And besides, if I add 2 dB of sensitivity to a speaker, when you're playing very loud, an extra 2 dB is not really noticeable. Even 3 dB, double the power, is not really that noticeable. You go, oh, it's a bit louder, but it's not stunningly extra loud. But that extra sensitivity has been paid for by having less bass, at least half an octave less bass. Well, when you listen to music, you always want to hear the bass, especially with a simple system. When you're a starter system, you don't want to be futzing about trying to add in a subwoofer. And so that's my choices.
Right.
So it gets down to, I do a reasonable, we'll get onto that, reasonable impedance, but a modest sensitivity, not a high sensitivity. But it's a real sensitivity level. And then I got bass. So you've heard all the demos where I always manage to get good extended bass from my boxes. It's not magic, but it is a design choice that I made right at the beginning.
Yeah. Well, you've explained it perfectly.
It's always easy,
I think I could design a speaker
but
now.
the answers are not necessarily easy.
Well, all right, that's right. You're over there and I'm over here. But here's a question about sensitivity. And I'm asking because I genuinely don't know the answer, and I'm hoping you do.
Right.
There is a perception, because we've been dancing, you and I, in separate coasts, have been dancing around this. Does the higher sensitivity design have greater perceived dynamics?
Okay, so if we look at either a 2- or 3-way speaker, let's take a 3-way speaker for example. So we split it into 3 bands. Because of what I'm showing there, there's only, for a given amount of bass and box size, there's only one sensitivity you can have. So So you've got to design, if it's not especially sensitive, you've got to design it to have very good power handling, so that when you're pushing a lot of power in to make it play loud, you're not getting dynamic compression.
Okay.
And that dynamic compression typically is from the voice coil heating up. So you'd be astonished at how hot a voice coil can get.
I was astonished when you told me. Yeah.
It can go up to 300 degrees centigrade, which...
In Fahrenheit?
Someone do that calculation. You guys are still on the old system. So it's probably 450 Fahrenheit. That's very, very hot.
For a woofer?
For a woofer.
Not for the mid-range, though.
It can do it for
Really?
a friend, but let's say especially for a woofer. So first of all, we've got to make all the materials withstand those kind of temperatures without failing or catching fire.
It happens.
Which happens.
Happened to me a long time ago, but it did.
Secondly, the problem is the voice coil itself has got a temperature coefficient of resistance. So that means at room temperature, it might measure 6 ohms resistance. But at that temperature, it's now going to be 12 ohms. So you're getting, it's drawing less current, so it's sort of not a perfect fail-safe, because you can still eventually burn it out, but at least it's trying to draw less power. It's saying, please, stop, please, I'm going to resist you.
But it is compressing.
But it does compress, because sensitivity is now dropped. And it's doing it dynamically as the music changes. So you get crescendos and quiet parts, but it's got a time constant to that. So you've been playing a loud part for a while, then comes the quiet part. It's still hot for another 10, 15, 20 seconds, depending on the design of the driver. And the problem with a speaker box, it's a beautifully insulated, closed environment. So once you have generated that heat, so now the background temperature is high, even if the voice coil wants to cool down, it's in an environment that is hot. Okay. So it takes a long time to cool down. So for that next quiet part, for 10 to 20 seconds, it's the wrong sensitivity level. And in a three-way system, since each driver's got different thermal characteristics, the frequency balance of the speaker is changing. So dynamically it's compressed, but spectrally it's changed. And on top of that, with a passive speaker, the crossover network is designed to work into a specific driving impedance. Well, if that's changed, it misterminates the network. So typically you take, let's say, a second-order filter, an inductor and a capacitor. You get it designed nice, smooth roll-off. You increase the voice coil resistance, and it now peaks before it rolls off. So you've got changes in level, you've got peaks in the response, and it's a mess. So it's always best to at least design the drivers themselves to be as efficient as possible. Now, when you talk about mid-range and tweeter, you don't have this low-frequency thing to worry about, because you're not working it down to its low-frequency resonance. The woofer you are, so not much you can do about the woofer except put bigger and bigger voice coils on and find ways to get the heat away. But with mid-range and tweeter, they don't have to be designed to be the same sensitivity as the woofer. Say you've managed to design the woofer to be 90 dB in that box. You could design the mid-range to be 100 dB and the tweeter 100, 105. And some of the tweeters I use, like the original debut, the tweeter at 2K was 105 dB sensitivity. It never gets hot. So you design it to be very efficient, then you pad it down in the network so that it never receives much power, and it never gets hot. It'll never suffer from dynamic compression. Mid-range, you're trying to do the best also. You're not tied up with that particular shape, and so you can play those games. Try and make it light, try and put a lot of BL on, and then at least mid-range and treble won't suffer from the same kinds of dynamic compression as the bass will. The only way to make things more efficient is to go bigger. And when we think, oh, horn loudspeakers, they're more efficient. Actually, they're not. If you take into account the enclosed volume of the horn, and if you were to do that with a direct radiator, configured with the right ratio of mass and BL to get the same frequency response as the horn loudspeaker, you'd have the same efficiency level. Now, it might not be practical to design one driver with the right combination of BL and mass, but theoretically, and Dick Small showed that in the paper, that they kind of come out the same. Physics is physics. It's very difficult to cheat physics.
I try.
Well, my motto for me is, it's not metaphysics, it's better physics.
Ooh.
Deep.